In this video, we are going to summarize the most important topic of probability chapter. What is probability and why we have to study probability? Probability is a measure of the likelihood of a random phenomenon or chance behavior occurring. How can we measure the likelihood that something occurs? In probability, we measure this likelihood by counting. For that reason, we need to study some counting rules at the end of this chapter. For example, if we have in a bag 10 balls, and from these 10 balls we have 2 blacks, the probability to get a black ball could be measured by counting. The chance to get a black ball is 2 out of 10 possible selection. The likelihood that we select a black ball could be expressed as a fraction, simplified fraction 1/5, or a decimal 0.20, or a percentage 20%. This measurement is associated with the fact to select a black ball from a bag that have 10 balls, 2 of them black. Then in 20% of the cases that we do this procedure, in 20% of the cases we are going to obtain a black ball. A probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. When I select one ball, I don't know which color I am going to select. It's uncertain. Doesn't matter that one outcome have a high probability, for example 99%, but when I repeat the procedure, it doesn't occur. It's possible, doesn't matter if have a high probability. In this chapter, we are going to study probabilistic procedure, and we are going to represent those procedures with this machine. Every time that we turn on this machine, we are going to obtain a different result. We are going to do exactly the same procedure, but every time that we do the same procedure, we obtain different outcome. In our example, we have the procedure consists in we have a bag with 10 balls. From these 10 balls, we have 2 black, and we want to analyze the probability to get a black ball. Always we have the same condition, 10 balls in a bag and 2 are black. Another classical example is when you throw a die. When you throw a die, you can obtain 1, 2, 3, 4, or 6. The sample space will be the set of all possible outcomes. In this case, will be 1, 2, 3, 4, 5, 6. An event is any subset of this set, of the sample space. An event, for example, could be get an even number when you throw a die. Then this event consists of these 3 possible results, 2, 4, or 6. That is the event to get an even number. The probability to get an even number in this case is given by 3 cases out of 6 possible results. Could be written 1 out of 2, or could be written 0.5, or 50% of the cases when we throw a die, we get an even number. To compute this probability, we need to count all cases in which we obtain an even number and divide it by the total possible outcomes in this procedure. The measurement of the likelihood that we obtain an even number when we throw a die is 50%. We obtain this measurement using the classical approach in which we assume that all outcomes have the same chance to occur. If the die is fair, all of the results can occur equally likely. However, we can manufacture a die in a way that one side have less chance to occur than others. In this case, it's no fair die. If you suspect that a casino have a die that is not fair, you can compute the probability using the empirical approach. How can you do the empirical approach? You need to throw a die a certain number of times. The bigger is the better. Then to compute the empirical approach for an unfair die, we need to do this procedure a lot of number of times, n times, and we need to write down the results. And after that, we are going to count the number of times that an even number appears, which is equivalent equivalent to the frequency of E, number of times that E appear in all of these trials, divided by the total number of trials of this procedure. Actually, in this formula, we need to substitute this equal by approximately, because the bigger is the number of times that we perform this experiment of this procedure, then the closer will be this relative frequency to the actual probability to get an even number in this die. But we can use relative frequency to approach the actual probability of one event. Remember, if the die is fair, all outcomes have the same probability, all outcomes are equally likely, then the probability could be obtained counting the number of ways that we can obtain from the sample space an even number divided by the number of outcomes in the sample space. That is the classical approach, and this is the empirical approach. In both cases, we compute the probability by counting. I told you we can use Venn diagram to represent all possible outcomes. The rectangle represents all possible outcomes, or the total number of tries that we did in one experiment, and this could be the event E. Then remember, each outcome could be represented by points here. In a statistic, we are going to obtain our data from the population measuring one characteristic, and we are going to plot our data in a number line to obtain distribution. But in this distribution, all points are organized according to its measurement. Then if we want to obtain the probability that one item have a measurement beyond this point, then we need to count all of these points and divide it by the total. That is the probability we need to count. But later we are going to show you that we are going to replace the operation of counting point by measuring area. Then we can compute the probability of a single event using either the classical approach or the empirical approach. But we can use the classical approach only when the probability of all outcomes are equally likely. But we are interested in the probability of compound event, not only single event, compound event also. For example, we want to compute the probability that A or B occur, or the probability that A and B occur. Let's use Venn diagram to explain these rules. Suppose that this is the sample space of one experiment or procedure, and all of these outcomes represent the event A, and all of these represent the event B. To obtain the probability that A or B occur is equivalent to obtain the probability that the union of these two sets of points. To compute this probability, we need to count the number of outcomes that are in A and add it to the number of outcomes that are in the event B and divided by the total number of outcomes in the sample space. We can split the denominator in this form, and the first fraction is the probability of A and the second is probability of B. Then to compute the probability of this compound event A or B, we need to compute probability of A independently, probability of B also independently, and we need to add both probability. We can use this formula only when A and B are disjoint, nor mutually exclusive like this. They have no common element, they have no common outcomes. The probability of A and B is another compound event is equivalent to the probability of the intersection of these two outcomes. We can represent this in Venn diagram in this way. Suppose that all of these points represent the sample space, and A is this and B is this other set. All outcomes that satisfy both conditions are located here. Then we need to count all of these points and divide it by the total. We observe in this graph that A and B are not mutually exclusive like in this graph. In this other graph, A and B are mutually exclusive. If we want to compute the probability of A or B when they are not mutually exclusive like this, we have to compute the probability of A. To do that, we need to count all outcomes that are here in A and divide it by the total. And also compute the probability of B. We need to count all outcomes in this region. Add it. But what happened with this? We have counted this outcome twice. For that reason, we need to subtract the intersection one time. And this is the general addition rule. We use this formula when A and B have common outcomes, and we use this other formula when A and B, the intersection is empty, no common outcome. To compute the probability of the intersection, we need to apply the multiplication rule. The multiplication rule states that the probability of A and B is equal the probability of A, and we need to obtain the probability of B, and we need to multiply these two probabilities. There is also a general multiplication rule. The general multiplication rule states to obtain the probability of A and B, we need to compute the probability of A independently and the probability of B given that A occurred first, and after that multiply these two probabilities. This probability is a conditional probability. Let's do one example of the multiplication rule. Suppose that we have in a bag 10 balls and 2 of them are black. The probability that we select one ball black is equal 2 out of 10. But what happens if we want to select 2 balls and we want both balls black? This procedure could be with replacement or without replacement. Let's do it first with replacement. Let's select the first ball, and after that we replace the ball, and let's select the second ball, and we want to obtain the probability that the first is black and the second selection also is black. If we do the procedure with replacement, my sample space always is the same. Then the probability that the first ball is black and the second ball is black could be computed in this way. We need to obtain the probability that the first is black, we need to compute the probability that the second also is black, and we need to multiply these two probabilities. In this case, the probability of the second selection is not affected by the first selection. These two events are independent. Then the probability that the first selection is black is 2 out of 10. The probability that the second selection is black, because I replaced the first selection, the probability that the second selection is black is the same, is 2 out of 10. Then the probability that the first selection and the second selection both are black could be obtained multiplying these two probabilities, and this probability is equal 0.04 or 4% of the cases. When we select 2 balls from this bag, both balls are black. Let's do the same problem but without replacement. We select the first ball that we want black, and we select the second ball that we want also black. The probability that the first selection is black and the second selection is black could be obtained multiplying the individual probability, but we have to do some adjustment because in this case the sample space will be affected when we do the second selection. We can write this in this way: probability that the first is black times the probability that the second is black given that the first one was black, because we want both black. The probability that the first one is black is 2 out of 10 possible balls. That is the situation when the first selection is black, because it's without replacement. Now we have 9 balls in the bag and my first selection was black. Given that condition, what is the probability that the second selection is also black? We need to do adjustment in the sample space, and the probability now is 1 out of 9 balls. And we multiply these two probabilities, which is equal 2 out of 90, which is equal 0.022 repeated, 0.02 repeated. In the first case, the two events are independent because the probability of the second event is not affected by the first result. However, in the second case, these two events are dependent because the probability of the second event is affected by what happened in the first result. Besides the addition rule and the multiplication rule, we have the formula for the complement rule. And also we have the probability of a conditional probability. A probability of A given that B occur first could be obtained computing the probability of A and B and dividing by the probability of B. This formula could be obtained when we isolate from this formula probability of B given A, the probability of B given that A occur first. When we send probability of A to the other side, we will obtain probability of A and B divided by probability of A. But be careful, probability of A given that B occur first could be different to this probability of B given that A occur first. Not necessarily these two probabilities are equal. In some cases could be equal. In this formula, B occur first. For that reason, when B occur first, we need to compute first probability of B and after that probability of A given that B occur first. Then in this case, this conditional probability could be obtained when probability of A and B divided by probability of B. Then this is a rule. When we compute the probability of a conditional probability, always in the denominator we have the probability of the event that occur first. Now let's review all formulas. In this video, we are going to put everything together. Which method do I use? Determine the appropriate probability rule to use. The first question that you have to ask is this: are you finding the probability of a single event? Could be a single event or could be a compound event. If it's a single event, if the answer is yes, it's a single event, then you need to ask the next question: are all outcomes equally likely? If all outcomes are equally likely, you need to count all cases, all outcomes where this event appear and divided by the total sample space, total possible outcome. That is the classical approach or the theoretical approach to compute probability. However, if all outcomes are not equally likely, then you need to ask this question: it is possible to get empirical data? Can we do this experiment? Can we do this procedure? If it's yes, then you can obtain empirical probability. You need to count the number of times this event appear divided by the total number of trials that you repeat this experiment. The bigger is the number of trials that you repeat this procedure, then the closer will be this probability to the theoretical or the actual probability. If you cannot do this procedure, then you need to do a subjective probability. You need to use a subjective probability. You need to use your experience, the knowledge about this event to forecast about this outcome. Then, if your event is not a single event, it's a compound event, then this compound event could be probability A or B, A and B, A given another condition, or could be at least. Let's study the first one. When the two events have this form, probability to get A or B, this is a compound event. We have the or. The two events are joined by the word or. Are the event disjoint or mutually exclusive is the most important question when you encounter or. Are mutually exclusive? If they are mutually exclusive, if they are disjoint, you can compute the probability of this event computing the individual probability and add it. That is the addition rule. The addition rule is related to the word or. If they are not mutually exclusive, they have common element, they have intersection, then you cannot count this intersection twice. To compute the probability of this event, you have to compute the probability of the individual event, but you need to subtract the intersection because you cannot count the intersection twice. If your compound events are joined by the word and, then you need to ask this important question: are the events independent? What is the meaning of independent? If this event is affected by the first one, then they are dependent. If it's not affected, it's equivalent to state that yes, they are independent. You can use the basic multiplication rule. You find the probability of E, find the probability of F, and multiply them. However, if they are dependent, then you need to compute the probability of the first one and the probability of the second one given even that the first one occur. That is a conditional probability. Probability of A given B, then you need to compute the probability of B, which is my condition, my new sample space, and the denominator should be the probability of A and B, the intersection. At least one means 1 or 2 or 3 or 4, then this is a compound event because at least one is the complement of none. Then you apply the formula for complement. Compute the probability of none and subtract this probability from 1.